Welcome to week 7. This week we have 2 videos, both of which are talking about second level, or what I prefer to say would be a group level fMRI analyses. Second level is a kind of term that SPM introduced, and I don't quite love it. I'll explain why as we go along, but effectively they mean the same thing, which is we want to talk about how we combine the data from individual participants' runs into an analysis where we have a set of participants, and then we can use the results of those analyses to try to make inference to the entire population, as opposed to just saying, well, what did this person's brain do in this particular task? So that's the challenge that we face this week. As I said, 2 lectures, both about 30 minutes. What I want to try to cover is I'm going to start by introducing this difference between what are called fixed effects and random effects models or analyses. Talk about the differences between them and how they're used. It turns out in many real-world scenarios, you're actually going to use a combination of fixed effects and random effects analyses. And as part of this, I also want to talk about linear contrasts, the role they play in terms of getting to the activation results that you're interested in. And then also the importance of inclusive masking. This is something that SPM introduced in the 90s, and it's just an invaluable tool for interpreting your data correctly. It's altogether possible to look at a result that was set up correctly. It uses the right kind of linear contrasts, but you could interpret it entirely wrong. And I'll go through that particularly in the second video with an example using a 2x2 factorial design, which is a very common and powerful way of designing fMRI experiments. That is to say, you have 2 factors, each of which has 2 levels, and you look for both main effects and interaction terms. So because that's such a common approach, I think it's worth going through that in some detail, and it's a really good way of illustrating the importance of inclusive masking. With that in mind, in this first video, I really want to focus on fixed and random effects models, what they are, what they're for, what you can do with them. So let's start by going back to the classic block design experiment that I always do, which is a block design finger tapping task. So that is to say, you're doing blocks of finger tapping followed by blocks of rest, and then more finger tapping, and then rest, etc. And you can see the design matrix for that shown here on the screen, with the left column going from light blocks of white to darker blocks of gray. The light blocks of white are the finger tapping task. The blocks of gray are the rest, so that's when you're not finger tapping. And you can see there are these little transitions in between because we took our block design and we convolve it with the hemodynamic response function, and of course you get this sort of rising and falling periods in there as well. So the first column is basically the tasks that we're interested in, finger tapping and rest. The second column is the temporal derivatives that we talked about last week. The temporal derivatives are included in order to allow for sampling jitter in terms of the timing. The fact that it takes 1 TR to go through the whole head, that might be 2 or 3 seconds, but it means that the data that you collect at the bottom is collected at a different point in time than the data that you collected at the top. We talked about this as something that you can correct in pre-processing using slice timing correction. But in practice, what I actually recommend is that you include temporal derivatives, and we correct it by removing any sort of systematic error there by increasing the complexity of our model. That is, adding another explanatory variable, in this case of no interest, that allows us to deal with that sort of temporal jitter. And then finally, the last column was all white because that's just a constant, which is the mean that we're going to remove from each run of data. And that's simply because the absolute values aren't very meaningful. All we're interested in is the changes relative to each other. So whether or not this person's mean is high or low is irrelevant. We're just going to take the mean out by including a constant term. Now, you'll recognize in this design matrix, I haven't included motion parameters or anything like that. It's really just to make things a little bit simpler in terms of the visuals that we're going to go through. But if you were doing it in practice, I would certainly recommend that you had 6 more columns in there, 1 corresponding to each of the 6 estimated motion parameters as well. Now, the thing that we're interested in this data set is comparing finger tapping to rest, right? That's the contrast that's most interest to us. We'd like to see what parts of the brain are active when you're tapping your fingers relative to when you're simply resting and not tapping your fingers. The way we do this is by using something called a linear contrast. These are also referred to as contrasts of parameter estimates, or sometimes abbreviated COPES, contrasts of parameter estimates. And they're used to sort of interrogate the statistical parametric maps and extract the information that's most relevant to us. And this isn't particularly complicated. You have what's called a contrast vector, which is just a row of numbers, one for every parameter in your model. And they tend to be 1, 0, and -1. In this case, we only need 1s and 0s because we have two parameter estimates of interest. We have the beta 1, which corresponded to that left-hand column, which is the finger tapping and rest. Beta 2, which is the temporal derivatives. That is to say, how much shift you need to correct your hemodynamic response function given that you've acquired the data at different points in time. Obviously, of those two parameter estimates, the one that's interesting to us is the first one, and we really don't care about the second. It's there to reduce structured noise that then doesn't go into the epsilon term of the general linear model, into the noise term. So if all we care about is parameter 1, then if you multiply the contrast vector, 1, 0, times the beta vector, B1, B2, then what you get is your contrast of parameter estimates, which is 1 times B1 plus 0 times B2. And the math doesn't get a whole lot easier than that. You end up with just simply B1, right? Now, the advantage to this is that's what we do at a single subject level. But what we're talking about today is bringing single subjects together into groups so that we can make inferences at the level of the population that the participants were drawn from. So let's just say in a simple case, we only have 8 subjects. And look, I picked 8 because I could fit some of these things easily on the screen. In practice, most fMRI studies would have something like 24 or more subjects at this point. So this is an illustration, not what you would actually do in real life. And in this case, what we want to do is we want to take the contrast of interest, which is finger tapping versus rest, from each of our participants and bring them together into a group model. So when you multiply that contrast vector across the parameter estimates for each person, because you're only getting beta 1 from each person, that's all we're taking up to the next level. We're taking beta 1 from each of our 8 subjects in this particular case. And what do we do with them once we have them at that second level or group level? Well, the first thing that we're going to do is the very simplest thing, which is just compute their average. We're going to compute a mean. And, I've put the equation here, but I'm sure every one of you is familiar with how you compute a mean. But in terms of the way I've written it out, it's worth pointing out that this is beta 1 from subject 1, which is B1, S1, plus the subject 2's beta 1, B1, S2, plus, etc., all the way through the number of subjects, and then divide by the number of subjects. So you take each person's beta 1 value, add them all together, and divide by the number of subjects. That's the mean. Straightforward. In addition, we need to compute the variance over the whole sample, and that's normally abbreviated with this sort of sigma squared here. So that is a little bit more complicated, but not a whole lot. If you just take each person's individual beta value, beta 1, and then subtract the group mean from it, and then square that, that gives you a measure of how far off this person is from the mean. So if they were exactly at the mean, there'd be no variance. If they're either higher or lower than the mean, you can't tell the difference because when you square it, the value becomes positive, and you add those together. So the further away all of your subjects are from the group mean, the more variance you have. Very simple. And again, I'm assuming that you've seen both mean and variance equations so many times at this point. If you haven't, the math is on the screen and it really isn't very complicated. And once you have both an estimate of the mean and an estimate of the variance, then we can compute a t-statistic. So we can start drawing statistical inferences from the data. And look, t at its heart is the ratio of the effect size, which is the mean, compared to the noise. And the noise, in this case, is the standard deviation, which is the square root of the variance. So just instead of being sigma squared, it's just sigma, divided by the square root of the number of participants that we have. Okay, so the noise reduces if you have a whole lot of participants. So as n gets big, you're dividing your noise by a larger number, and therefore you get less noise. The importance here is not the equations. It's the fact that the statistic that we're interested in, this t-value, is larger if the mean is larger, so if your effect size is big, and it's larger if the noise, the denominator, is small. So those are the two things. It's the ratio of the effect size to the noise, okay? And this is, nothing could be simpler, right? This is really, really basic sort of descriptive statistics, and then as you apply them to sort of inferential statistics to get these kind of t-scores out of it. And what do you get? Well, then you get an activation map. You have these t-values in each of the voxels in your brain, and you put some threshold on it and say, okay, what would be significant above, say, 0.05? Well, then which are those voxels? And I can show them here in two different ways. On the left, I'm showing them in what's called a glass brain. So this is a visualization that's a bit of a pain in the neck to get used to, but it's very useful when you do. So the idea here is that 3D visualization is tricky. So we're going to give you 3 2D visualizations. Now in the glass brain, what happens is, so for instance, in this top left corner, you can see it's a sagittal slice. All that means is that you're looking through the head in one direction and you can't see left, right. So it's all collapsed into one plane. Similarly, the second one is a coronal slice. And again, you can't see front to back. It's all been collapsed into a single plane. And then the third one, which is sort of below it, is an axial slice. And again, you can't see top to bottom. It's all been collapsed. Which means that in any one direction, you're missing a dimension. But as soon as you get used to putting them together, you can sort of see where these activations are. In this particular example, the activation's essentially in primary motor cortex, and that's it. That's where the big gray blob is. So it's very easy to visualize these things. In practice, I don't find glass brains the most useful way of doing things. So I tend to prefer to put the activations on the anatomy and not collapse over those dimensions. I want us to see what's happening at this plane of this anatomy. So that's what's shown on the right. So there's the subject structural scan. The activation is shown there. And for instance, you can possibly see that those crosshairs are directly behind the central sulcus, which means, they're directly behind the precentral sulcus. Which means that they're on the precentral gyrus, which is the site of primary and sort of secondary motor cortices, right? So this is the subject's hand area related to their finger tapping. And that's it. One of the things that's worth pointing out in these visualizations is we're only ever showing visualizations as one-tailed t-tests. So I'm not showing both where there's more activation for finger tapping and where there's more activation for rest. I'm only showing half of that. The question that I'm interested in is what's going on when I'm finger tapping. I'm not interested in also saying, well, what's going on during rest that's more than finger tapping? That's a different question. So as a result, by default, functional imaging studies typically just use one-tailed visualizations for all of these things. That'll be relevant when we talk about inclusive masking, which is why I bring it up. Okay. So at the group level, the important thing that's different between the different types of analysis is the way you handle variance, right? So a mixed effects or a random effects model incorporates both within subject and between subject variance. So the two main sources of variance in your experiment. One is the variance that the individual subject goes through in the run. So you get an estimate of what's happening in that run, but sometimes they're more or less active when they're doing finger tapping. So there's some within subject variance there. In addition, there's variance between people. So whether you're a good activator for primary motor cortex and I'm a bad one or whatever, those things all end up producing between subject variance. And the two sources of variance, both within and between, are things that we want to take into account. When we do a mixed effects model or a random effects model, and I'm going to use those terms essentially interchangeably, then what we're doing is we're assuming that the participants are a random sample of the population and that they're a reasonably good sample, and therefore that estimate of the variance between subjects is a reasonable estimate of the variance across the whole population. And therefore, any conclusions that we draw from those data, we can generalize to the whole population. In contrast, when we're doing a fixed effects model or fixed effects analysis, then we're going to throw out between subject variance and only make use of the within subject variance. The importance of that is if you only consider within subject variance, then the inferences that you can draw are specific to the participants in your experiment. That is to say, you cannot generalize to a wider population because you've thrown out the between subject variance, which is what allows you to generalize to that larger population. Instead, what you can say is, look, this is what's happening in this set of participants, and that's perfectly fine, but is very much more limited, as you can imagine. For the most part, what we're interested in are mixed effects or random effects analyses because they allow us to make some sort of larger conclusions about the data. However, there are circumstances where a fixed effects model may be very helpful for us, and we'll talk about two of those as we go along. So let's start with the mixed effects model, or random effects, because this is what we normally want to get to. And as I said, the full variance that we're interested in here is a combination of the within subject variance, which I'm going to abbreviate as sigma squared with a little w for within subject, and the between subject variance, which is sigma squared with the b. So the full variance is a combination of those two things. Okay. The within subject variance comes from the first level analysis. So that is to say, if you're in the scanner and you're doing this finger tapping task for 5 minutes, the within subject variance is within that 5-minute period, right? Because that was when you were in the scanner doing the task. So it's within subject. The between subject variance comes from the fact that you have multiple participants in the scanner. Okay, and that's when we talk about this higher level analyses. That's when we combine the data from the cross participants into a group level analysis, which, as I said, sometimes SPM refers to these as second level analyses, because at the first level they would consider being the subject specific analysis. The reason I don't love that is because it assumes that a subject specific analysis means that that person only had one run. So for instance, if you're doing a finger tapping task and it's as simple as A, B, on off, then maybe 5 minutes of finger tapping is fine. But the reality is lots of tasks are complicated and take a long time, and as a result you don't want your subjects to fatigue, so you don't run them in a single run. So let's just say you were convinced that finger tapping was what you really wanted, but 5 minutes of data isn't enough. You want 30 minutes of data. Okay, well, you can run a 30-minute run, but my goodness, you're going to fatigue your participants, and it's not an ideal thing to do. And therefore, you're going to increase the within subject variance because they're just going to get tired and basically stop paying as much attention and doing it as seriously. In contrast, you could run it 5 times and only have 6-minute runs, right? So in 6 minutes, they're probably fine. Then you give them a bit of a rest, you talk to them, and then you say you're ready to do another, and you collect 5 of these 6-minute runs. In that case, what you need to do is you need to combine the data from that individual into a model of the subject, right? So you're not interested in combining to a larger sample, you're only interested in that participant. They just happen to have run the task 5 different times. In which case you're going to use a fixed effects model to do it, and you'll combine the data and make an inference to say, well, this combination at a fixed effects is what this subject is doing, which is a perfectly adequate use of a fixed effects model. That's exactly what you want to do. But by definition, when you've done that combination over the individual's run, that's already a second level model, right? Because the first level was 1 run, the second level was those 5 runs, and then the third level will be combining all the individuals in this experiment into a group study. That's why I don't really like referring to this as a second level analysis, because it's slightly misleading depending on the assumptions of your design. In any event, let's move on to that. So as I said, if you were to do a fixed effects model, then that would assume that you're just going to dump the between subject variance. And one of the reasons that we don't do that is that in fMRI, typically the between subject variance is significantly larger than within subject variance. That is to say, the differences between people swamp the differences within an individual. They're both there, they both contribute to the variance. But if you dump the larger source of variance, then you're getting rid of the single largest source of variance in your analysis, which is a strange thing to do, unless it's specific to the question that you're interested in. So in this case, when we're combining across, say, 5 runs of 6 minutes each within an individual, that's a perfectly valid thing to do because it's the same person. There's no point in considering between subject variance since it's only one subject. And the inference that we want to draw is, what is Joe's activation like when he's doing this task? I don't care about the population as a whole because I only have data from one person, Joe in this case, right? So that would be a typical use of a fixed effects analysis on the way to doing a group level analysis. But there are times when people conduct fixed effects analysis across individuals. And when you do that, you can get results that are very much dominated by an individual participant's data, right? Because you're not considering the fact that different people are doing the task slightly differently and there's variance there, you're ignoring that aspect of variance, then your statistics can be overinflated because you've reduced the denominator in your t-test, right? So the variance is less than it should be. Therefore, the significance is too high. The only other time, other than the example that I've given you about combining an individual's data across runs, that you might use a fixed effects analysis is if there's a very, very small sample of people to draw from. So for instance, imagine you're working with a patient population that's very rare. And in the UK, there are 23 of them, and within London, there are 6, and you are somehow managed to get all 6 of them to do your task. It's just not feasible for you to collect the other, 17 across the country or, however many are around the world, because that's just the way it is. It's a very rare population. In that case, given the small numbers, you would probably conduct a fixed effects analysis because you don't have enough participants to successfully estimate between subject variance. With only 6 people, there's just not enough information there. In that case, you would probably use a fixed effects analysis. But you'd have to be very, very careful when you were talking about the inferences that you could draw from it, because the inference you could draw is that within this group of 6, these are the results that I see. I can't tell you whether this generalizes to the population that they're drawn from or not, because I don't have enough data about the between subject variance. Let me try to make this, try to illustrate this using a non-fMR example. And this comes from the Poldrack book, so if you've already read that chapter, you've probably seen it. But look, this is about hair length. Right? And the idea is that we have 2 groups here. We have men, which are shown in blue, and women, which are shown in that sort of pink color. And all it's showing is the hair length in inches from 0 to 16 inches on the x-axis. And on the y-axis, we're just seeing that there are 8 different people. There are 4 women and there are 4 men. Right? The first thing that hopefully you can see is that the distribution, if you measured every length of hair on a person's head, there's going to be a distribution, right? Some of them are shorter than others. And those distributions across all 8 people are assumed to be identical. That is to say, if the length varies, but the pattern is basically the same. You're still seeing this kind of bell-shaped or normal distribution. So as a result, the within subject variance is in that normal distribution, right? It's, if you measure all the hair lengths in a person, you can compute the mean and you can compute the variance of their hair length. What differs across these people and across the groups are the means, not the variances here that we're talking about. And you can see that on average, if you just look at the 4 men in the 4 blue curves, that on average the means are less than the women. The women are to the right, the men are to the left. And if you ignored the between subject variance, then what you would get is an estimate of the curves that's shown there on the fixed effects line. So fixed effects by definition is we're going to ignore between subject variance. All 4 of those men have the same shape distribution. So all we need to do is find the mean of those 4 values, and then you can see because the distribution are the same, as you get more participants, so not 1 but 4 in this case, the variance reduces, you get a tighter curve. So the fixed effects analysis there shows a really strong difference between male hair length and female hair length. And it's true, with these 4 people, you can see that there's a big difference in the length of their hair. That's a fixed effects analysis, and it's fine for this, this population. If all I'm going to care about is these 8 people, yes, there's a difference between the men's hair length and the women's hair length. In contrast, if I were to say, look, let's see, I'm going to estimate how much variance there is across people, because you can see that the means for men and women individually vary, right? This one guy has something right on the mean, one guy's a little bit to the right, one guy's a little bit to the left, and the same for the women. So there's variation in terms of how long men's hair is, and there's variation in terms of how long women's hair is as well. And if we take that between subject variance into account, then we can look at the mixed effects line, which is the bottom line. And now you can see the means are exactly the same, but the variances are much higher. Why are they higher? They're higher because we're taking into account both the within subject variance and the between subject variance. We're taking into account the fact that there's much larger variance across individuals than there are within individuals. And now those two curves, you can see, overlap quite considerably, and it's a little bit harder to tell whether there's a significant difference between men and women's hair lengths just based on this example. That is exactly analogous to what we're doing when we consider a fixed effects analysis versus a random effects or a mixed effects analysis. And it's all about how we treat the variance. It turns out that estimating between subject variance, sigma squared b for between, is actually tricky. One way to do it is to just assume that the within subject variance is essentially identical across participants. And we can kind of get away with this because I already said that between subject variance is actually the variance that dominates in fMR. So if we just make this kind of semi-plausible assumption that the within subject variance is small and therefore basically we can assume it's identical across participants, well then we can use an ordinary least squares approach, which is probably something you've seen if you've taken statistics classes in the past. If you haven't, I don't really want to get into ordinary least squares other than to say it's very computationally efficient. It's a very fast way of calculating this, but it's based on some assumptions that may or may not be true. And the problem is that when we do an ordinary least squares approach, it can lead to a loss of statistical sensitivity, our ability to detect real activations, but in certain weird circumstances, it can actually end up producing what amounts to be a negative variance. And by definition, if you remember the equation I gave you, we were squaring all those values. There's no way you can square a number and add them up and get a negative value. And yet, sometimes if we make this assumption, that's exactly what effectively happens. And I'll go through both examples. The alternative, which is absolutely by far a better option, is to just sort of estimate the between subject variance. And computationally, this is a significantly more difficult task. It involves estimating these variances and refining it and going through this sort of iterative process. But if you have that information, it's much more statistically sensitive. It's not subjected to this kind of negative variance problem. And it'll allow us to do something called weighted linear regression, which I'll explain in just a minute, which is really advantageous. And as I said, I'll explain it in a minute. Okay, so I mentioned that an ordinary least squares approach potentially can lead to this loss of sensitivity. And what I'm showing here in this slide is an illustration of that. This is the finger tapping task. With just a relatively small number of people. In this case, I have only 8 participants. And I've analyzed the exact same data using ordinary least squares to estimate between subject variance and using the fMRI model, which does this kind of more sophisticated iterative process. And what you can see is that if you look at the bottom line, which is using the fMRI random effects version, then you actually get really nice activation in and around primary motor cortex. Whereas if you look at the ordinary least squares solution, you basically don't detect this. Why? What's happened is using ordinary least squares, we've overestimated the between subject variance, which means that the denominator of our t statistic is too large. It's larger than it should be. And if you look at the ratio of the effect size to the overly inflated variance, then the t statistic is reduced. It doesn't pass threshold. You've lost sensitivity. And this is a fairly common example. The downside of using ordinary least squares is that you're very likely to lose statistical sensitivity. Given how hard and painful it is to design these things, collect the data, pay for all the time, etc., losing sensitivity is a real cost, and it's something that you need to be concerned about. In practice, years ago, like 20 years ago, when all this stuff was being developed, computational power wasn't as readily available as it is now, and ordinary least squares was a quick way of getting things done. Trying to do the more computationally intensive thing sometimes took days to weeks to actually compute those values, and as a result, sometimes people were willing to just chuck that out and say, forget about it, give me the OLS solution and I'll just run with it because I can't wait 7 days to get until my computer's done this calculation. The modern era with the computers that we have available, probably the phone in your pocket is significantly more powerful than the average workstation computer was 20 years ago. It's less of an issue. People normally use the more sensitive solutions. As I said, there's also the possibility of this kind of negative variance issue. And this is an unusual scenario. It really only happens for a very small sample of subjects. So if you have more than about 12 participants, the idea that you'll get negative variance is very, very unusual. But for a long time, that wasn't a huge number of samples, right? So for the early years of fMRI, tended to have like 6 to 12 participants. That was not unusual. It's no longer the case. As I say, now we typically have 24 or even more participants, so it's less likely to occur. But what you can see here in this example is that, again, what I've done the same thing. I've analyzed exactly the same data in 2 different ways. And the ordinary least squares solution is on the top row, and then the more sensitive iterative process is on the bottom row. And what you can see is there's clearly overlap between those, which is probably legit activation. But there is additional activation, particularly around the brainstem in the ordinary least squares. And I'll just highlight that in the video as we go through. That's not in the more sensitive version. And that's almost certainly false positive due to this negative estimate of variance. So it isn't really computing a number that's negative. It's just that it's computing a number that turns out to be smaller than the number that you would get with just within subject variance. And if you do that, the only way that can happen is when you add the within subject variance to between subject variance and get something smaller. That means the between subject variance had to have been negative. So it's effectively produced this kind of negative estimate, which is obviously an error, but it's a consequence of these small n's. The long and the short of that is, and the reason I went into this, is because ordinary least squares is probably a solution that makes sense because you've seen it before and it's a perfectly plausible way to proceed. There are risks to doing it because the assumptions that were made are routinely violated by the fMRI. At first glance, it seems like it's a sort of a sensible approach, but in practice, it's not. There's no reason to use OLS these days. The computational power is such that the computers are more than capable of doing even very large fMRI analyses in a sort of reasonable amount of time. So if you only have 20, 24 subjects, you can assume that it's not going to take more than a couple of hours to run them all through the analysis, assuming you're working on a modern machine. On the other hand, if you've got like 100 or 130 or something, much larger, then it might take you a couple of days, who knows? But even so, like if you were thinking about testing and running 120 subjects back in, say, the late 90s or early noughties, then you could assume that your poor computer is going to chunk away at it for like a month. And if you made an error in the way you set that up, then you'd have to fix it, and it would be another month before you got your results. That's just no longer the case, thank goodness. Okay, so what we actually use is what's called a weighted linear regression. And now we do this kind of iterative process that estimates both the within and between subject variance in a much more unbiased and plausible, valid way of doing it. It's computationally intensive, but it doesn't matter because that's kind of happening behind the scenes. If you're really interested, there are multiple different ways of doing this. So SPM uses a Bayesian approach, whereas FSL, which is the Oxford software, uses sort of more of a Monte Carlo approach. But one way or another, you converge on the same solution. It just takes you a little bit more time and computational power. The advantage to doing this is we no longer have to assume that within subject variance is the same across all of our participants. And if you get an accurate estimate of within subject variance, then you can weight the way you combine the data into your group analysis. So that is to say, let's just say you have 20 participants and 2 of them, for whatever reason, weren't that engaged in your task. So sure, they're doing their finger tapping, but they're not really paying attention to when it starts and stops, and they're thinking about other things. And as a result, they have quite a bit more within subject variance because they weren't really doing the task that well. Well, do you want to weight them the same as somebody who did the task brilliantly and was spot on and paying attention? Or do you want to sort of take into account that there's greater variance in those subjects, so we're going to downweight them when we bring them all together into the group level and add everybody up and compute the variance? That's the main advantage to doing this kind of iterative process and estimating the variances correctly. It allows us to do this weighted linear regression, that is to say, a weighted combination at the group level. And that means that we can downweight the people who didn't do the task very well in terms of their imaging data and increase the contributions from those people who were sort of spot on, whose variance was very low. And that means that we can get a better, more valid, more realistic estimate from the data that we've actually collected when we try to make an inference to the entire population.